You know, there is this moment when you are working on an engine or maybe fixing a heavy piece of machinery where everything just clicks.
Oh, absolutely.
Like you tighten that last bolt, you step back, and you can practically see how all those gears and shafts are going to work together to turn raw power into motion.
Yeah, you can put your hands on it and it makes complete physical sense.
Right. And today we are taking that exact same hands-on mechanical mindset and applying it to something massive for this deep dive. We are looking at the story of wind power.
Which is such a great topic because I think a lot of people see these giant white towers on the highway and think it's some untouchable futuristic mystery.
Yeah, exactly.
But based on the stack of research we have today, it's really not. It is essentially old technology made new. It's just an ancient tool that humans have continuously adapted to do our heavy lifting.
And that mechanical intuition you use when, working with tools or construction, that is exactly what you need to understand this.
Yeah, it's the exact same logic. We're going to track how simple physical forces have been scaled up to power the modern grid.
From the very ancient roots, right up to the nuts and bolts of how these machines actually work today.
And honestly, it is wild to think about how long humans have been doing this.
Oh, it really is. I mean, we're talking over 5,000 years ago with the first sailboats on the Nile River.
About 1,000 years.
Yeah. And our sources even mention the Babylonian emperor Hammurabi. He was using wind power for irrigation projects way back in the 17th century BC.
Wow, that long ago.
Yeah. When you break it down, early mechanical windmills were really just, well, sails tied to a stick.
Right, taking the boat sail and just anchoring it to the ground.
Exactly, just to do the backbreaking chores.
Which is a brilliant piece of engineering, especially given the resources they had. If we look for the world's first known practical windmills, we actually have to travel to the Sistan region.
The Sistan region.
Yeah, it sits right between modern-day Iran and Afghanistan. This was around the 7th to 9th centuries. They built these things called Paneman mills.
Oh, keep anemone. How did those work?
So they were horizontal windmills, meaning the sails rotated around a central vertical pole. Think of how a revolving door spins.
Oh, sure. So the pole goes straight up and down.
Exactly. That's the axis they used. They would cover these wooden frames in reed matting or really tough cloth, and then they'd build walls around them to channel the harsh prevailing winds directly into the sails.
So the wind hits the reed mats, turns the central pole, and that pole goes straight down to, what, a heavy grinding stone.
Right, a heavy grinding stone for grain or a wheel to pull up water.
Man, that is just a direct transfer of mechanical force.
It really is. And from there, the technology scaled up dramatically. By the 14th century, the Dutch were using wind power for massive civic engineering projects.
Right, I read about this. They built these highly advanced windmills specifically to pump water and drain the flooded Rhine River Delta.
Yeah, they were connecting these wind-driven shafts to massive scoop wheels and Archimedes screws. They literally reclaimed dry land from the sea using nothing but the force of the wind.
Which is just an incredible leap in scale.
It's survival engineering at its finest.
And you see that same kind of survival engineering later in the 1800s and 1900s right here in the American Great Plains.
Oh, the multi-bladed steel windmills.
Exactly. Those iconic ones you see in old westerns. Millions of them were built to pump well water for isolated farms and cattle ranches.
Because they had all those tightly packed blades.
Right. They needed massive low-speed torque to pull heavy water up from deep underground, even when the wind was barely blowing.
They were an absolute lifeline out there. Without that simple mechanical water pump, large parts of the American West simply could not have been settled.
But, that highlights a major shift in the timeline. Because for thousands of years, the wind is just a mechanical workhorse.
Right, it pushes a boat, it turns a heavy stone, it lifts a bucket.
But a physical push is very different from an electric spark. Oh, completely different.
So how did we make the leap from spinning a wooden wheel to actually, powering a light bulb?
Well, that pivot happens in the late 1800s, right at the dawn of the electrical age. The first real breakthrough was in 1883.
Okay.
An Austrian inventor named Joseph Friedlander installed a wind turbine at an electrical exhibition in Vienna.
But instead of connecting the spinning shaft to a grindstone,
He connected it to a dynamo.
which is an early type of generator.
Exactly, to charge batteries.
And the stories from our sources about these early inventors are just incredible because they were fighting both engineering challenges and public perception.
Yeah, people were terrified of electricity.
Right. In 1887, a Scottish professor named James Blythe built this massive 33-foot tall turbine with cloth sails right in the garden of his holiday cottage.
Just right in his yard.
Right in the yard. He used it to charge batteries and power the lights in his house. And he even offered his surplus electricity to the local town to light their main street.
And they turned him down, right? They actually turned him down. They told him they thought electricity was the work of the devil.
I mean, which makes sense if you put yourself in their shoes.
Really?
Yeah. For all of human history, energy was something you could see. A fire burning, a horse pulling, a water wheel turning.
Oh, that's true.
Suddenly, this man is creating invisible energy that travels through solid metal wires, and he can start a fire or shock you if you touch it. People were deeply suspicious.
That is a great point. But, that suspicion didn't stop the inventors. Just a year later, in 1888, an American inventor named Charles Brush built an absolute giant of a machine in Cleveland, Ohio.
I saw the pictures of that in the sources. It was huge.
This wasn't just a science experiment. It was a true feat of heavy engineering. It was 60 feet tall, and the rotor alone was 56 feet across with 144 individual blades.
Wow.
And it successfully powered 100 incandescent light bulbs in his mansion, plus some electric motors in his laboratory.
What Brush and Blythe figured out was the crucial link. They mastered how to bridge the gap between mechanical motion and electrical generation.
But how does that actually happen? I mean, I can picture a shaft turning a gear, and I can picture a gear turning a pump. But how does a spinning metal rod create invisible electricity that you can send through a wire into a house?
So it all comes down to the inner workings of the generator.
Okay, break it down for us.
If you open up a generator, it is surprisingly simple at its core.
Mm.
You have that central metal rod, the shaft, which is being turned by the wind.
Right.
Attached to that spinning shaft are heavy, powerful magnets. And surrounding those spinning magnets, close but not touching them, are thick coils of copper wire.
Wait, so you just have magnets spinning in a circle inside a copper tunnel?
That's it, exactly. Right. And the physics here relies on a principle called electromagnetic induction.
Electromagnetic induction.
Yeah. When you physically move a magnetic field past a conductive metal like copper, that invisible magnetic force interacts with the copper at an atomic level.
It pushes the electrons.
Yes. It physically pushes the electrons inside the copper, forcing them to move from one atom to the next. And a continuous flow of moving electrons is exactly what an electric current is.
That is fascinating. It is entirely mechanical.
Completely mechanical.
It's exactly like a car's alternator. Or, you're just taking an electric motor and running it in reverse.
There's a perfect comparison.
Because in a power drill, you pump electricity into the motor to force the magnets to spin the drill bit. But in a generator, you use external force to spin the magnets, which forces the electricity out.
Exactly. And this brings us to what I like to call the big secret of the global power grid.
Oh, I love this part.
Almost every power plant on Earth operates on this exact same principle. They're all just different ways to spin a shaft.
Think about that. When you look at a coal plant, a natural gas plant, or even a nuclear power plant, what are they actually doing?
Boiling water.
Right. They are just burning fuel, or splitting atoms, to boil water. That water turns into high-pressure steam, and that steam blows past a turbine to spin the shaft.
Yep. And hydroelectric dams do the same thing, but they use the weight of falling water to spin the shaft.
It's all the same trick.
The end goal is always just spinning those magnets near the copper wire. Wind turbines just skip the fuel and they skip the boiling water. They let the wind do the mechanical spinning directly.
And for anyone listening right now, understanding this basic mechanical principle is incredibly valuable.
Absolutely.
Because maintaining these generators, fixing them when a bearing wears out, troubleshooting the wiring, that relies on hands-on experience with mechanical components and tools.
Real-world skill.
Yes, these are real-world, highly skilled jobs, and they are well-paying jobs that absolutely do not require a 4-year college degree.
Not at all.
If you know your way around an engine block or a construction site, you already possess the foundational mindset for this industry.
That is such a crucial point. The physics might sound complex on paper, but the daily work of keeping the grid humming is deeply grounded in practical mechanical trade skills.
So, okay, the generator is the exact same technology whether you are burning coal or catching wind.
Right.
Which means the engineering bottleneck is the fuel source. With coal, you just shovel more into the furnace, but wind is messy.
Very messy. It's chaotic.
Yeah, you can't put it in a pipe. So how do you actually design a machine to catch enough of it to match the force of high-pressure steam?
Well, that is the core engineering challenge of wind power, And to understand it, we have to look at a German physicist named Albert Betz.
That's B-E-T-Z, right? Betz.
Exactly, Betz.
Right.
In 1919, Betz proved a physical law that governs every single wind turbine designed today, known as the Betz limit.
The Betz limit?
Right. He mathematically proved that even a flawlessly engineered wind machine can only capture a maximum of 59.3% of the wind's kinetic energy.
Wait. 59%. That
Right.
sounds incredibly inefficient. I mean, if I built a hydroelectric dam that only caught half the water flowing through it, I would be fired.
You'd definitely be fired.
Or an engine that just dumped 40% of its fuel. Why is the physics so different here? Why can't a perfectly designed fan catch 100% of the wind that hits it?
I know. It is totally counterintuitive, but it comes back to the physical space the air occupies. Think about it like a traffic jam on a highway.
Okay.
If your turbine caught 100% of the wind's energy, it would mean the wind transferred all of its speed into the blades.
Right.
So the air would literally drop to 0 miles per hour the second it touched the turbine.
Which means it stops moving.
Right. It would create a solid wall of dead, motionless air directly behind the blades.
Oh, I see.
And if there was a wall of dead air behind the turbine, then the new wind blowing in from the front has nowhere to go.
It would just pile up.
Exactly. The incoming wind would just deflect and flow completely around the outside of the turbine instead of passing through it.
Wow.
So you have to let about 40% of the wind's energy pass straight through just to push the old air out of the way and keep the traffic moving.
That makes perfect sense. You have to leave enough energy in the wind so it can physically get out of its own way.
Exactly.
So knowing that you are fighting this 59% bottleneck, engineers have come up with some incredible designs to catch as much of that allowed energy as possible.
They really have.
And it isn't always just a giant propeller. Our sources detail these things called vertical axis wind turbines, or VAWTs.
Yeah, VAWTs.
These spin on a central vertical pole pointing straight up at the sky, kind of like a merry-go-round.
Vertical axis designs are brilliant in their simplicity, primarily because they can catch wind from any direction.
Oh, right, because they're a circle.
Exactly. If a storm rolls in and the wind suddenly shifts 180 degrees, a vertical turbine doesn't care. It just keeps spinning.
So our sources highlight two famous vertical designs. The first is the Savonius rotor. That's Savonius, pronounced Suvohneus.
Suvohneus.
Yeah.
Right. The Savonius rotor operates primarily on a physical force called drag, which basically just means it gets pushed by the wind.
Like a sail.
Sort of, yeah. Imagine taking a 55-gallon steel oil drum, cutting it in half straight down the middle, and then offsetting the two halves slightly so they form an S shape if you look at it from above.
Like two heavy scoops waiting to catch the air.
Exactly. When the wind blows, it gets caught in the open scoop on one side and physically shoves it forward. It is an incredibly rugged, simple design.
I can imagine.
Now, a Savonius doesn't spin very fast, but it generates massive torque.
A huge amount of twisting power.
Right. That makes it perfect for heavy mechanical tasks like pumping water or grinding, even if its slow speed makes it less efficient for generating grid-level electricity.
Okay, so that's the Savonius. The second vertical design mentioned in the sources is the Darius rotor. That's Darrieus, pronounced Darius.
The Darius design looks entirely different. It is often called the egg beater turbine.
The egg beater.
Yeah, because it has these long, thin, curved blades attached at the top and bottom of a central shaft. And unlike the Savonius, the Darius operates on aerodynamic lift.
Lift. That is the exact same force that allows heavy airplanes to fly, right?
Precisely. The blades on a Darius turbine are shaped exactly like airplane wings.
Oh, wow.
As the wind flows across the curved surface of the blade, the air pressure on one side drops. And, nature hates a vacuum. So this pressure difference creates a force called lift, which pulls the blade forward, causing the whole central shaft to spin.
So it's being pulled, not pushed.
Right, because it uses this aerodynamic pull rather than just getting shoved blindly by the wind. A Darius turbine can actually spin much faster than the wind itself is blowing.
Which is incredible engineering.
It really is.
But, while vertical designs like the Savonius and Darius are really clever, if you drive past a massive wind farm today, you don't see giant egg beaters or steel drums.
No, you don't.
You see those massive white towers with horizontal axes spinning like airplane propellers.
Standard three-blade design.
Right. So if vertical turbines don't have to face the wind, why did the horizontal propeller design win out for the modern power grid?
Well, it ultimately comes down to scale and altitude. Horizontal axis turbines can be built much, much taller.
Okay, and taller is better.
Yes. The higher you go into the atmosphere, the stronger and steadier the winds become. You get free from the friction of trees, hills, and buildings.
That makes sense.
But to capture that high-altitude wind and convert it into stable grid power, these horizontal giants require some incredibly heavy, highly intelligent machinery.
Let's look at exactly how they do that, because this is where the hands-on mechanical stuff gets really cool.
Oh, definitely.
Up at the very top of those massive steel towers is a rectangular housing called a nacelle. That's Nacelle, pronounced nacelle.
News cell.
From the highway, it just looks like a little pod behind the blades. But if you get up close, a modern nacelle is often the size of a school bus, and it weighs hundreds of tons.
Hundreds of tons, because that school bus-sized nacelle holds the entire mechanical powerhouse of the turbine.
Right.
So the three massive blades connect to a central hub, and that hub turns the main shaft entering the front of the nacelle. But remember, those huge blades are spanning hundreds of feet. They spin relatively slowly, maybe 10 to 20 rotations per minute.
Which is nowhere near fast enough to generate grid-level electricity. I mean, a generator needs thousands of rotations per minute to work efficiently.
Exactly. So positioned between that slow main shaft and the high-speed generator, there is a massive gearbox.
And this operates just like the transmission in your car, but doing the exact opposite job.
Tell me what you mean.
Well, in your car, the engine is spinning furiously, right? And the transmission gears it down so your tires turn at a manageable speed.
Right.
But in a wind turbine, the gearbox takes the slow, massive, heavy torque of the spinning blades and gears it up, converting those 15 rotations per minute into the 1,500 rotations per minute the generator needs.
And the engineering required to handle that much raw torque without shearing the gear teeth is phenomenal. You have the main shaft, the gearbox, and the generator all bolted in a row inside that nacelle, suspended hundreds of feet in the air.
It's wild. But as we mentioned earlier, the wind doesn't just blow from one direction.
No, it constantly shifts.
And a horizontal turbine has to face directly into the wind to work. So how does a machine that size adapt to a shifting storm?
That is where the sensors come in. On the roof of the nacelle, there are two key instruments constantly reading the environment.
Okay.
First is the anemometer, A-N-E-M-O-M-E-T-E-R, pronounced anemometer.
Otter.
It looks like little spinning cups. Its only job is to constantly measure the wind speed.
Got it. And the second instrument?
Right next to the anemometer is the wind vane, which tracks the exact wind direction. These instruments act as the eyes and ears of the turbine, feeding constant data down to the control computers.
But finding the wind direction is only half the problem, right? Once the computer knows the wind has shifted from the north to the east, how do you physically turn a machine that weighs as much as a locomotive?
That is where the yaw system comes in. Y-A-W, pronounced yaw. Yaw simply refers to rotating left or right on a vertical axis. At the very base of the nacelle, right where it meets the top of the tower, there is a massive ring gear.
Almost like a giant steel turntable.
Exactly, a turntable. And mounted on that ring gear are heavy-duty electric yaw motors.
Okay.
When the wind vane senses a change in wind direction, the computer activates the yaw motors. The motors engage with the teeth of the ring gear and physically slowly rotate the entire massive nacelle until the blades are perfectly facing into the new wind direction.
It is an absolute symphony of heavy machinery. I mean, you've got anemometers reading the speed, computers telling the yaw motors to rotate the housing, the blades catching the lift, the main shaft transferring the torque, the gearbox stepping up the speed, and the generator turning it all into electricity.
That's incredible when you stack it all up.
It really is. And again, think about what it takes to build and maintain this equipment. Calibrating a yaw motor, replacing a sheared gear in a high-torque gearbox, inspecting the structural integrity of a steel tower. This requires serious mechanical and construction know-how.
Absolutely.
If you have experience fixing engines, running heavy tools, or doing structural construction, you already speak the physical language of these machines.
It is a highly advanced industry, sure, but at its core, it is fundamentally mechanical. It relies entirely on practical, hands-on trade skills to keep it running.
So just mapping out the journey we've been on today during this deep dive, wind power is not a new fad.
Far from it.
It is an ancient technology that evolved from grinding grain in Persia to pumping water in the Netherlands and the American West, all the way to the highly advanced smart giants that are powering the modern electrical grid.
And we learned that every power plant is essentially just a way to spin a shaft.
Right. And wind turbines do it by catching the kinetic energy of the air, constantly fighting those physical limits of how much energy they can extract before the air jams up.
The bet's limit.
Exactly. But if we connect this to the bigger picture, our 5,000-year history with wind is still evolving. We mentioned that today's standard is the horizontal axis turbine with massive blades. But what if the future of wind energy doesn't use massive spinning blades at all?
Oh, this is where the boundary layer concepts from our sources get really interesting.
Yeah, tell them about that.
So there are experimental designs being tested right now that completely rethink how we interact with the wind. For example, the bladeless Tesla turbine.
Bladeless.
Yeah, it doesn't use angled blades to catch the wind. Instead, it uses the natural friction and viscosity of air clinging to tightly packed flat metal discs to drag them into a spinning motion.
That is wild.
Or consider something called the wind belt.
Oh, the wind belt is fascinating because it doesn't spin at all.
Right. It generates electricity just from the high-speed vibration or aeroelastic flutter of a taut strap in the wind.
It is exactly like holding a blade of grass tightly between your thumbs and blowing on it to make it vibrate.
Exactly.
Mm.
Generating grid power just from the high-frequency fluttering of a tension strap.
Wow.
It just shows that even after thousands of years, we are still finding entirely new physical mechanisms to put the wind to work.
Mm.
It really raises an important question for you to mull over.
Yeah.
What will the wind technology of 50 years from now look like?
Yeah. What's next?
It may be as fundamentally different from today's massive spinning giants as today's turbines are from Hammurabi's irrigation mills.
That is a wild thought to leave on. Well, to wrap things up, in our next deep dive, we are going to get even more hands-on. We are going to mentally open up a modern turbine to see exactly what is inside and how all these massive components fit together to keep the grid humming.
I can't wait for that one.
So the next time you tighten a bolt or fix a machine, remember, you are tapping into the exact same mechanical logic that is out there right now, catching the wind and powering the world.
Absolutely.
Thanks for listening. We'll see you next time.